Hi, I'm Nex, and welcome to our 11th lesson, the inverse functions. So in today's lesson, we will learn what inverse functions are, how to find them, and basically how to make sure if one function is an inverse of another. So before I begin, about the Among Us collab stream that I had last week, I have about 10 hours of 3 different footages and pretty much no time in my life. So I will need a while to get to it, but when I do, I promise I will make it the best as I can. And that will probably be some time before New Year, hopefully. But yes, without any further ado, let's get right ahead into our lesson. Oops. So, the first question we have to ask ourselves, just like in every lesson, what is an inverse function? Well, if this is a function, so f of x is some y, then the inverse would be g of y is x. So we need a different function than the other one, and when we put in the y, we get out the x as the input, here treating y as x and x as y. To avoid confusion with marking and graphing, let's use a different notation. This f to the power of -1 is read as inverse of f of x and does not mean 1 divided by f of x. So basically, we know that a function takes some input, then gives us out some output. An inverse swaps this, taking the supposed output and giving us the correct input. An example would be like putting on socks. To put on a sock, you usually have your foot still and pull the sock up. An inverse would be holding the sock still and pulling the foot out. I am aware that I may be weird for having this as my first example, as most people don't overthink how they put on socks, or they do it a different way. I just thought that this example might help. Of course, a small but important thing to mention is that a function, so f of x, has to be injective. So if it does not pass the line test, which means that there's always exactly 0 or 1 intersections with a graph, it will not have an inverse. Anyway, let's visualize this step by step, and we will start with x. We put that x into our given function, and we get y. Now we take y and put it in an inverse function, and we get the original x. So our job with this process is to figure out what this inverse function is. So what it does to the variable we put in, and how can we graph it. And that's what we will learn today. For our example, let's have x as 3 and y as 10. Now here I could tell you about one property that we will see later visually, which would allow me to find one of the inverses just with 2 values by making up my own function. But for this example, our function will be 2x plus 4, meaning that if we put in 3, we would have 2 times 3 is 6 plus 4 is 10. So our inverse function has to change 10 into a 3. So let's use our knowledge of equations to help us. For that, we have to isolate x, as that is the quote-unquote y, or output of our inverse function, while y would be our x, so input. This is all confusing, so don't worry, we will isolate x. So first we subtract 4, and then divide by 2. Now, because when we graph a function, we still follow the same coordinate system, and if we do not do anything to this, this is just equal to the original formula we had. Meaning, we had to switch out y with x and x with y. So we can put it all in the same coordinate system. Now remember, this isn't the exact correct order of the steps, it was just us trying to figure out how to do it on one easy example. Now here's the comparison between our f of x, so the red line, and the inverse of f of x, so the blue line. Some of you may see something about this comparison, and even if you don't, that is completely okay. That's why we are here, and we will take a deeper dive in a bit after we get there. Right now, all that we wanted was to see how a simple function can be transformed in its inverse, and how do both of them look on a graph. So basically, we found an inverse of this red one, and we got this blue one. Now, let's figure out how to actually do the math of finding the inverse function. First step here would be that we take our equation where y is written in terms of x, for instance y equals 3x plus 4, then we will switch their places, so we will replace x with y and y with x, basically giving us an equation of x written in terms of y, so y becoming the dependent variable. Then we solve for y by isolating it just like we have when we were drawing or when we were solving equations. And lastly, we change the y into the inverse f of x, and that's it. A simple three-step rule. Swap the variables, solve for y, replace y with f to minus 1. Let's solve some examples. We will start with linear functions and then forward with those that we know are injective. It is important to note here that real inverse functions are those whose original is injective. However, we can still technically get an inverse set from one that isn't. So we can still do the steps, but that won't really be an inverse function. Or we have to redefine that original function so it is injective. But we will get to that in this video, don't worry about it. So our example is y is to x plus 5. We swap the variables, we isolate y, and that is our formula. So the black one is our inverse and the purple is the original. Since we have a rational function, we have to be careful that it passes the line test. That only happens when the vertical asymptote is odd, as we only have 1, 0 in the q of x. This means this is an odd asymptote, and this means that the signs will change, which means that there will always be a maximum of 1 point intersecting with the horizontal line if we move it from bottom infinity to top infinity. For this one, if you graph it, you see that it does not have multiple intersections, so we are free to take the inverse. So I replace f of x with y, I switch the variables, multiply the denominator to the left to get rid of the fraction form, then I isolate every term with y in it on the left and the rest on the right. Here I multiply this entire equation by minus 1, so I get rid of the minuses on the right. And with that I switch the order here because minus 1 becomes plus 1 and plus x becomes minus x. So this is ordered like this. Then I divide with 1 minus x, and this gives me the formula. So red is our f of x, and green is our inverse. Now, on this example, it's even easier to see the property. That property is called the mirroring effect. Well, depends on the language. Here, we call, well, in my school, we call it the mirroring effect, but it might just be different. But yes, we see that the red one rises here and then continues rising here, while the green one, the inverse, rises from here and then from here. So if we compare how these points are, we see that they're mirrored over a certain line. Now to see the graphical background of this, as most of you have seen or noticed or understood from my reference, that the inverse of the function is equal to what we would get if we mirrored our original function over the line y equals x, which kind of makes sense. Because if you think about it, we swapped y with x and x with y, so it makes sense that something like that could happen. So inverses are mirror images across y equals x. Our next rule is that if we take an inverse of x, so here, and we put it in the normal function, so f of x, we would get x. Same thing if we put the function first and then the inverse over it. It may seem like a super logical rule and all, but in reality it's a super good failsafe if you're not sure. Just like with y equals x squared, one would assume that the inverse is y equals square root of x, but since we aren't on the root functions, I'm gonna solve that example later, and you're gonna see exactly why that's not the case. But yes, there you could put this rule to the test and actually see if that's true. For any two functions, you can see if they're actually inverse of one another. So basically, when you solve it all, you should get x equals x or 0 equals 0. That's how you know that one is the inverse of another. And lastly, only one-to-one functions have inverses, which means that they are injective. So horizontal line test, injective ones are those that are one-to-one, and only they have inverses. Now let's see exactly how to tackle a function that isn't injective. Let's take a look at x squared plus 1. Since it's not injective, we will restrict our domain to x is greater than or equal to 0, so it passes our test, just like this. Now let's see how do we continue with this. Our first step would be to swap our variables, which, important part, we also have to swap them in the conditions. So if we had a condition of x is greater than or equal to 0, after the swap we have to change the condition by replacing x as y. Next, we just isolate the y by subtracting 1. Then we take the root. Now, since we're taking a root because we're looking at the default value of y, we have to add plus or minus. However, this is where the condition comes in handy. The condition states that the number will always be non-negative, meaning that we do not have to add a negative sign because, well, out of the root, you do not get a negative number, unless some very specific cases that we will not cover anytime soon. But that means that there's no need for a negative sign, meaning that only positive results will come out of this. So this simplifies our result, as this is our function. So this is our result, and let's use the rule from before to verify that this is actually the inverse of this. And this is how it would look like. So I colored the inverse with orange and the normal with purple. So I will just basically put this in instead of inverse of f of x, and then this instead of f of x. So I put it all in. Now we have to apply that this in this bracket is equal to x, and we have to put it in, for the first example of course, in the purple one here. So if this is all x, we have to square this entire bracket and then add +1 on the end. As for the second one, we have to put this purple expression instead of this orange x here. So this would look something like this. Hopefully you can see how we did it. So we take this as x and we get the same formula, and we take this as x, we get this formula. Now, since we have a huge mess, let's clean it up so it's easier for us to see this. You can try using a fixed value or just calculating with x's. I found using a fixed value slightly easier because sometimes you may get complex binomials and everything, and that's just a mess to work with. But let's say I use x is 5, so I put in the 5s, so x squared is 25, x are all 5s. Now 5 minus 1 is 4, and 25 plus 1 is 26. Now taking a square root of 4 is equal to 2, and 26 minus 1 is 5. Oh, sorry, 25. God damn it, math. And then we square the 2 from before to get 4. And then taking the root of 25, we get 5. So 4 plus 1 equals 5, and 5 equals 5. So yes, since both conditions are correct, we know that we did find the inverse correctly. So this is the inverse of this. Now, this lesson was a lot shorter than usually, but it is a topic that is nice to know even if it's not that massively filled with information. So here is the mini test. It's also again shorter than usual ones. I just had to get this topic out because I really think this is something important that everyone should at least know what it is. In general, I don't know if it's gonna help us anytime in the future, but just in case it does, I'm gonna give it. Just like with the vectors, we're gonna do that when we get into physics. I don't know if I'm gonna put that as a physics lesson or a math lesson, but I'll see when I get there. I'll probably have it like under the physics chapter, but still put it in the math playlist because technically it is a math thing, but it's gonna help us understand physics so much better. But yes, again, thank you all for tuning in to this short video this bi-week, and hopefully the mini test solving goes well, and if not, you're welcome to join our Discord, which is the first social link down below. And if you have any questions, I'm relatively active there and I'll gladly answer them all for you. So thank you again, have a great rest of the weekend, and I'll see you all on our next quest. Bye!